So we are going to pick off where we left off from last time. And so we were looking at an example data set. Oops, fread, not frad. This data set is a data set of wages. We looked at, as a quick refresher, we looked at what's in this data set. We have earnings and then a couple different attributes. We started off last time looking at a linear model of, it's, I think, our first sort of real example using data and sort of walking through interpreting, and our model diagnostics ultimately ended up getting us to transform the data a little bit and to filter out some of the data so that we were getting decent residuals. And so if you guys remember, I'm just going to sort of copy and paste this from last lecture. We kind of arrived at this data set, which we felt fairly comfortable because in terms of bias in the residuals, because we ended up finding something where you generate a relatively, I would say, random set of residual points when we're plotting our predicted values against the residuals. And so this, you know, compared to some of the other residual plots that we were making, I think is probably a fairly decent sort of representation of the data, or sorry, of the non-random, or of the non-bias estimates in the model. And again, when you kind of do this filtering where we take out some data points, it's always important to sort of recontextualize the results so that what we are finding here in our summary of the model, that this is all kind of described relative to the quote unquote new data set. In other words, these are sort of the average effects that we would describe between earnings and any of these individual variables for people who are not having, you know, these small sort of part-time jobs, which brings down a lot of the these estimates when you have the full data set. Okay, great. So I actually want to take this wage model and we're going to go back and actually kind of simplify a bit in order for us to demonstrate the concept of the interaction variables, and also to help solidify our understanding of the dummy and categorical variables. So the first thing I'm going to do is we are going to go back and sort of simplify the model. I'm actually going back to the original data set where we're not cutting out the 1500. In the context of what I'll be trying to show, it doesn't actually make a difference. And so that's why we're kind of including some of those data points that we had cut out before. Okay. So let's take a look at this. So we have summary wage model 1. And so we had a description of this from before. Right, so this indicates that that males make $21,748 on average more against the baseline, and the baseline is your intercept. So you start, the starting wage on average is $24,246. And that represents the category that's not being represented here. In other words, for females, the starting wage would be here. You can actually explicitly decide what the baseline value should be. So if you had like male or female, or if you were doing some other category. So for example, if I want to do wage model other, just really quickly to show race. Hispanic, other, and white, and the baseline. And so in this case, the baseline is black. And the way that the baseline is chosen is actually just alphabetical order. So in male, female, F comes before M, and so that gets chosen, and then B comes before H, O, and W. So that's kind of the default here.
I was just typing a message too. Your screen is frozen for me as well.
Oh, it's frozen. Oh.
Yeah, like from line, your cursor is on line 9. So I thought it was on my end, but it looks like it's happening to others.
Okay, it seems like everyone's frozen. Let me, maybe if I stop sharing and share again. Okay, hang on. Never had that happen before. Okay, how about now? Is everyone able to see?
It looks like it's still loading.
Okay.
Still loading.
Oh yeah, it's still loading on my, I have it on my iPad too. It says still loading. Huh, that's, well, that's gonna be problematic. Let's see. I feel like it can't be my internet though, because I'm on campus and I guess you can still see my camera recording. Oh, did that show up now?
Yes.
Okay, cool.
Yeah.
Okay, where was I when we froze? I can walk back a little bit.
So for me, I didn't see what you typed into line number 9. I didn't see that before.
Ah, I see. Okay. Okay, so yeah, we'll jump back. So line 9 is just doing a simple regression of earnings on the gender. And so if you look at the results of that model, you basically just have earnings against gender, and you have male and your baseline, and the male indicates, okay, you make $21,000 more, and in the baseline for females, you start at 24,000. So let me kind of draw what that looks like. I wonder if I can do this. Okay. So dev.off is a way of just clearing out the plotting window. So here we have wages, and the results are just, so this is our intercept, and this is at $21,700. Okay. And then up here we have, what is this? 21,748 plus, excuse me, plus 24,000. So this is going to be approximately 46,000 here. And this just indicates for males, and this indicates for females. Okay, and so when you have a dummy variable, you need to keep in mind, you need to keep in mind that this is not indicating the earnings for just the males. It is the additional earnings above the intercept. So the interpretation is a little bit different. I think if you kind of look at this chart here, it's kind of the best way to sort of qualitatively think about it and interpret these results. So the example that I was giving here is that if you do it with race, you also have the 3 here, and then your intercept is your baseline. And then the point that I was making before is that the choice of the baseline in this one is, you know, black, and in this one it's female, and that has to do just with the alphabetical order. When you do the factors, unless you specify otherwise, the default first entry will be the one that's chosen as the baseline, and because it's done in alphabetical order, it'll look like this. If you want to choose a different baseline, then you have to reorder your factors. And so, for example, if I wanted to do that, I could do something like this. Levels, where I say, let's say I wanted white to be the baseline, then you could do this. So I think this should work, and this will make it so that the first entry is white. And if I look at the summary again, you should see that being reflected. Oh, yeah, it is. It adds all this extra text, unfortunately, but you can see white, black, Hispanic, other. I'll actually change it back. So if you actually you know, do this to the original data, then you won't see all of this crazy amount of text, instead of like including it in the equation line. So let me delete this part just so we can see it a little bit better. Okay, I'm going to now, I'll draw 2 plots right now to demonstrate like different ways of kind of interpreting this set of results. So I'll draw it kind of identically to what I had before for the female male version. So it'll be something like this, wages. Okay, and let's actually start at the baseline. So I'll just put that right here. So this is 28.3. And if I draw out a line that looks like this represents our baseline income, which is Black. Okay, and I'll actually draw this in different colors now. So Hispanic minus 2,800, and so that'll be, let's just say here, that will be about 2,600 or 26,000, right? It's 28,372 minus 2,887, and so this line represents Hispanic. And then we have other, which will be about $4,000 more. So let's just say about 32. I'm not very good at drawing straight lines, but just imagine that that line is straight. So this is other. And lastly, we have, if you're white, so plus 5,000. So let's just say approximately 33,000. That one's better. Okay, so this is essentially what's kind of happening here. Now, let's now look at the standard errors and the statistical significance, the probabilities, and you'll see something kind of interesting going on here. The intercept is very statistically significant, and that means that this line here, we say, is statistically different from 0. And so if I were to look at the standard error, it's $2,780, okay? And you could kind of reflect that difference. I know that the scales are going to be slightly off, right? But it means something like this. So you have some kind of error bars. So one standard error would be plus or minus 2,780. Two standard errors would be, plus or minus 5,560, right? It's 2,781 times 2. And so you can see that it would take, 10 standard errors before you got to 0. And so that is what that means. But the other lines actually indicate a difference from your intercept. And so this 2,800 is actually telling you how different it is, whether or not it's statistically different, not from 0, but from the wages for Black under race. And so what you can see here is that it's minus 2,887 plus or minus 4,500. And so 95% of the time, your red line might look something like this. Oh, okay, wait, that's too big. Sorry. My scales are really off, right? So it'll look something like this. So it isn't telling you anything about how different it is from 0. It is telling you how different it is from your intercept point. And so what we could say here is that compared to the average income for someone who is Black, if you are Hispanic, you do not have a statistically different income. And that's same for other races as well. But actually, if you are white, then you're saying something like less than 10% of the time, do white people actually have an income that is the same or lower than if you are Black. And so, yeah, the interpretation of these statistical significance, remember, for these dummy variables and for categorical variables always goes back to your reference. And the sort of alternative way that I was mentioning before about how you could interpret this is actually something like this, where this is wages, this is your intercept. If we set this at 0, and then you would have, what did we have? Minus 2887, Hispanic. Then you have 3905, other, and lastly, 4993, white. And then now you can see that these are being compared to a 0 point, but that 0 point is gonna be your intercept, which you reinterpret at 2800. So the main thing is that the comparison of the statistical significance is still being done against the intercept. All right. Any questions about that? This is definitely one of the more confusing ones if you, in terms of interpretation, if you haven't seen this before for dummy and categorical variables. So definitely, make sure to review the notes if this is not straightforward.
Could you repeat the interpretation for the white category? Is it, I think you said that less than 10% of the times.
Yeah. So this number here tells you the probability that that this particular coefficient is equal to 0 or less. So the way that you think about that you often think about these types of things is your estimate of 4993. So this is white wage compared to Black wage. Okay, let's say, so this is 0. Sorry, it's a little bit off, right? But okay, wait, I'll do that again. Okay, so these values are never, this 4993 is never just like a static value. It is the average estimate of the wage, but there's a sort of distribution. And let's suppose hypothetically that this value was 0. What that would mean then is that if the value were 0, then it would mean that there's no difference between the average white person's wage versus the average black person's wage. That's the kind of interpretation. And so because it's at 4,993, we say on average, white people make $4,900 more. But because it's a distribution, some of the time you could actually observe that that the wage is the same or even less. That's the whole point of the statistical significance, is that this tells you how often that happens. So 1.77 1.7 times the standard error times below is going to be when that happens, which is equivalent to 8.85% of the time. So just by sort of random chance, if we think about the sort of value of the coefficients in this distribution, 8.85% of the time, it will be not any different from or less than, the black wage. As opposed to in the interpretation for like a Hispanic and other, they're saying, almost half the time it's going to be not any different. So that's why we say that those are not statistically significant.
That makes sense. So basically this area on the left side, the one that you shaded,
yep,
that should be 0.0885, right?
Correct. That is correct. Yep, exactly. Great. All right, so let's now do something like this. Earnings against education. So this one, hopefully at this point, folks will be sort of fairly comfortable with interpreting and sort of understanding. So this is our regression results for our earnings against education. So every additional year of education yields a $4,500 or $4,490 increase in your annual earnings. And so if we were to draw this, it might look something like this. So this would be education and X, sorry, no, not X, what am I doing? And wages or earnings. And you might have a line that looks like this, where this is negative 27,525.2, and slope is equal to 4490.7. Okay. And this line helps to show you that as you increase the years of education, the corresponding amount of earnings and wages that you get increases, right? By sort of this increment. And now we can we can essentially make this a little bit more complex and integrate these two variables together. So earnings, sex plus education. And what this tells us is that now let's figure out the model where we include the education effect, but also the gender effect. And so if I take a look at the results here, it looks like this. Okay, and so let me kind of draw the graph to show what this looks like. So our first model, right, looks something like this. Male, female. And then our next model looks like this. Wages, or not wages, sorry. Education. So the third one will look like this. Let me actually move that up. So this is going to be education, years, and earnings. So we're going to start at negative 3880. So this is negative 38.8 thousand. And I'm going to draw a slope up like this. And then I'm actually going to have another line. So this is for our intercept, which is our base female. And then I'm going to have another line 2430 above. So this will be negative negative 21.4, right? So that's going to be, oh, sorry, I made a typo here. So this is 31.8. So 31.8 or negative 31.8 plus 20.4. So this will look like this. Okay, so you have two parallel lines, and it's analogous to what you see in example 1, but instead of just flat slopes, now you have the slope for education. And so you have education as an effect, and then genders as separate, essentially kind of intercepts, right? And so your plot ends up looking like this, where you now have two parallel lines with the same slope, with intercepts indicating the average differential between your earnings by gender.
Shouldn't be the number below the intercept be 20.4?
It should be, remember that everything is relative to the baseline. So this number is calculated as negative 31880 plus 2430, which
Yes, it should be 11.
Oh, sorry. I'm bad at math. This is what happens when you try to calculate things on the spot. Sorry. That's right. So 11.4.
Thank you.
Yeah, so this should be negative 11.4. Whoops. Yeah, so, okay, hopefully that wasn't super confusing for everyone, but right, again, you're just recalculating the intercept based off of the baseline plus the value of the coefficient that you're interested in. Okay. So now, this is, so you can, hopefully you can all see kind of the representation and build up of what we're doing here. So we are now sort of combining both continuous variables and discrete explanatory variables together and seeing how you interpret them in the model. There is also at the end yesterday we also talked about interaction variables, right, which are relationship among variables that is not additive. So in the context of this problem, the way you might think about an example of this is that, okay, so I have this difference between the average that males earn money and females earn money. And then I also have this average effect of education. I can include both of those and see those linear effects. But what if there is something happening where the effect of education based on your gender is also different? In other words, it's not just an additive effect, but you may have some kind of interaction happening between the education and gender in addition to what you're seeing here. Okay, and so we'll show this sort of last example, and I think that the graph will help sort of really make this point clear. Of the difference between the interaction variable and what we've shown so far. So this time I'm going to have education. Okay, let's do same orders. Sex plus education plus an interaction term between my education and gender. And so if you simply multiply the variables together, it can sort of figure out how to do this. And behind the scenes, what's happening is that you have this column of genders that's just like ones and zeros getting multiplied against the actual value of the education. Okay, so wage model 4, summary wage model 4. All right, so we have our intercept term, which is the female intercept, the male baseline, and then education. And now we have this extra variable, sex male education. And so let's explain kind of how this works. So just really quickly, that's our first example. Our second example, education. And then third example is going to be, education here, male, female. Okay, so this last one also going to be slightly different. Okay, so I will now draw a line like this. So this is going to be our baseline. It's going to be female. And then this intercept is negative 22.4 thousand, and the slope is equal to 3522.3. And now we're going to look at the male, and what you actually see. So this is going to be analogous to your intercept, and this new term is actually the change in the slope of your education term for males. And so we're actually going to have, like in our example 3, 2 different lines, but now they're no longer parallel, because what we've tried to do in this model is essentially say, does education, does the effect of education on earnings actually differ between males and females? And so we've interacted that term together and we can see what happens. So in the intercept term, you end up with negative, so approximately negative 26,000. And you guys can double check me on this, but this should be 22380.7 minus 3945. Okay. So you're actually starting lower now, but you end up with a line that might look something like this. So males, and this slope is equal to, the slope should be equal to 3522.3 plus 1815.7. So that will be what, 4,300. So this is approximately 4.3K compared to my 3,500. And so what this tells you, right, is that for every additional year of education, oh, sorry, I'm bad at math again. This is 53, not 40. Okay, so this is telling you for every additional year of education, a female starts to make $3,500 more, but a male will make $5,300 more per year of education. And so you can hopefully see how we've built up from our model 1, 2, 3 through 4, how this changes, and the interpretation is going to be slightly different. Okay, any questions here?
Oh, sorry, go ahead.
Sorry, just a quick question. So when you do the sex times education, that's like it's a multiplicative operation, like it's like zeros time, it's multiplying zeros to all the female data points.
Yep.
Okay.
Yeah. Let me show you actually what's going on. So let's say you start on a table that looks like this. Let's see. So education and sex. So let's say it's 1, 2, 3, 4, and then you have M, M, F, F. What is happening behind the scenes is this. It goes education, and then so F becomes the baseline. So it's only going to do this for males. So it'll be 1, 2, 3, 4, 1, 1, 0, 0. And then it's going to do education males and then education times males. So it'll be 1, 2, 3, 4, 1, 1, 0, 0, 1, 2, 0, 0. So this third table is what happens behind the scenes when it makes this. It'll omit one. It'll omit one of the columns. And that's actually a mathematical property. Otherwise, the matrix that it solves for is singular because you have perfect explanation of everything, of all the variation. So if you had 4 categories, it would do it for 3 categories and so on. If you have 2 categories, it'll do it for 1. And then the regression will be run on that last table. So that's kind of what's happening behind the scenes. Okay, Aditya, you had a question.
Any reason why in model 4 the being male coefficient becomes negative? Because in all the other models we had that being male makes you better off in terms of the earnings.
Yeah.
And it's only in this model that the coefficient flips. Is there a particular reason, or how does one interpret?
It is because that is how the data looks. And let me be maybe a little bit more explicit about that. So let's suppose you have, so I'm going to draw data in like a couple dimensions here. So education, and let's do so let's do something like this. Hang on. So let's say these are my data points. And if I were to draw a fit through them, let's suppose that I have to draw a fit where the lines are parallel. Then my fit might look something like this. Actually, maybe it'll be, actually, okay, I think that was probably all right. Maybe like this and like this. And that is an artifact of the fact that by constraint, your model is saying that the slope of the education has to be the same for the 2 points or for the 2 categories, right? But if I allow the lines not to be parallel, in other words, if I think that education essentially has its own slope for each gender, then you might see something like this, right? So the fact that it is, more or less is purely kind of an artifact of the data. It is how the data is sort of best fit to it, and that in itself, like the intercept, is not kind of a realistic measure anyways, because no one has kind of 0 years of education in the data that we're looking at. And in fact, if I do this, right, education, right, the first quartile is starting around 12. And so if I started at 12 times 5,000 and 12 times 3,500, you know, they're both going to be sort of positive. And in fact, I think that's 5,300. So actually 12 times 1,800. Yeah, so that'll be very actually close to the intercept, which means kind of right at the first quartile, males are already kind of starting at the same level as females, and then that sort of growth is increasing.
Yeah, got it. So what's
yeah.
important is basically the slope, right? And that's the critical.
Yeah, exactly. Whether or not you think that there is a difference in the slope by gender, or if it's kind of its own independent effect, and then you have like just two parallel lines.
Yeah.
Yeah.
Thank you.
So if you do the regression like separately on all the data on female and male, would that be the same result?
So yeah, actually good question. So if you did wage.male, wage.female, so your question is, if I do this of education data equal wages, sex equals female, and then here it would be this. So the question is whether or not, essentially, if I run this model for the red separately from the blue, if I get the same results. And so I haven't done this before. I think in this case you would, but let's have a look. And yes, that's right. So 3,500 and 5,300, which is what we were saying, right? 3,500 and then 5,300 is the sum of these two, and then negative 22,380 minus 4,000, so that's 2,600 or 26,000, so negative 26,000, and then 22,380. So yeah, exactly. In this particular case, you would separate. It would look identical to the separate ones. Now, if you added more variables into it, then it becomes connected again. You can't just separate them because you're calibrating to essentially more data that is independent of the gender. If we're all tied to gender, then it would look the same. Yeah, but good insight. Sarah, did you have a question?
Yeah, I actually have two questions.
Uh-huh.
So the first one is, whenever we run a model with an interaction term, are we required to also include the non-interacted? Like in this case, we have to include sex and education so that we can have the interaction term of sex with education?
Yeah, so you are asking about this essentially, wage model 5, if you could just do this, right? Or, you know, or one of them and not the other, right? Is that what you're asking?
Yeah, exactly. If we have to include both terms, like, is it valid to only include like sex and then the interaction term?
So let's look at what happens. If I include sex times education with just the interaction, all of them will sort of pop back up. And yeah, the reasoning for this is actually because any of the sort of categorical variables requires in your sort of complete set your baseline, and so that it ends up putting everything back in automatically, because without it you would be essentially like missing data to calibrate on. So yeah, the basic answer is yes. You do. This is like a shortcut for putting in everything, but in general practice, like we often say, write it out explicitly so that you understand kind of what's going on.
Okay, yeah, that makes sense. Thank you. And then my second question is, are there any tests that we can use to look at our data and see if there are two variables that should be interacted with each other, or is that primarily based on intuition? Because I feel like every time I've learned about it, it's based on intuition, but then sometimes in practice, that's a little bit easier said.
Yeah. So I will say that usually it is kind of based on intuition, and the reason for that is actually a little bit more complex, and we actually kind of delve a little bit into this when we talk about sort of complexity of models, but yeah, like you would imagine that, hey, you could have some kind of algorithm that can help determine whether or not two variables together, or even three variables together combined, have some kind of nonlinear effect that you could capture by doing this interaction. And in fact, you can do this, right? You could look at whether or not there is, if you like multiplied two variables together and you made a graph, and you looked at the sort of relationship between your now interacted variable term with your response variable, your y, you could see whether or not it's like random or whether or not there's like a trend. And that would be a way of like quantitatively being able to say there's an effect. So where the problem starts to arise, it's actually not that you can't do this, it's that it rapidly, very, very, very quickly becomes impossible to systematically do this. So, and so why is that? X1, X2, you have two variables and one combination, right? One combo. So X3, we have three variables, and now we have X1 and X2, X2, X3, X1 and X3, and then X1, X2, and X3. So now you have four combinations and four variables. You have the same number of combinations from before, right? But plus one extra set. So it should be times 4, right? So now you have 16 combos and then 5 variables. So hopefully you can see kind of where we're going here. And it really, really rapidly becomes totally impossible to do this depending on your sort of data set. And that is why when people say, okay, you just have to use your intuition to think about this, because it is because that intuition ends up being one of the strongest filters for not looking at every sort of possible combination. Yeah, and so unfortunately, that the answer is kind of like, you can't algorithmically brute force a way of kind of sussing out which interactions are important. You kind of have to just end up using your intuition on that.
Thank you.
Mm-hmm. Okay, let's take a quick break. Yeah, and yeah, we can continue with questions if anyone has any, but yeah, definitely feel free to take a quick break here. Okay, so let's continue here. The next sort of topic that we're going to be talking about is actually related to Sarah's last question, which was about, you know, how we can decide essentially which interactions to choose. And so that's actually a more specific version of the question that I want to sort of introduce everyone to, which is the sort of the more general one, which is how do I even know which variables to put into my model? And so this is a principle known as model selection. And this essentially tells us how do we select variables to include in the model. So we can even think about the wages example that I gave, right? We were looking at education and gender, but there's also, what else was there? There was age, there was height, there was race, and like, why not choose some of those other variables? And in what combination of the variables will I actually have sort of quote unquote the best model, right? And so we're gonna, starting next class, we're going to start to look at a couple sort of really standard techniques of doing model selection. But today, and sort of for the rest of the lecture, I wanted to introduce a sort of higher level concept that helps to think about how you can go about figuring out the sort of goodness of a model. So we've covered some metrics. We talked about the f-stat, the r-squared, the sort of mean squared error. And those are all sort of nice metrics that tell you about the quality of how the model that you have created fits against the data set, your existing data set, and they measure it in slightly different ways, right? So the r-squared is like, how much variation does it capture? The f-stat is like, oh, how does it compare against, a model with just with all the betas equal to 0, so it's kind of like a comparison against a sort of mean thing. And then the mean squared error is like the average of the essentially like size of the residuals, right? What is the average size of the error against your fit? So these are all like different ways of comparing your fit to the data that you train the model on. But actually, there is a concept known as out of sample validation. And kind of over the years, when I think about sort of the quality of a model and its ability to predict something or to represent a real relationship, to me, they're ultimately really what you want is for your model to be able to correctly estimate a value, right? What you can ask yourself, kind of what is the worth of a model where like I kind of statistically am confident in the results, but that if I ever apply the model, that it never tells me the right answer, right? And so this is kind of the crux of out of sample validation. And the whole idea is if I calibrate my model to some data and I just compare it to the data that I trained it on, of course it's going to do kind of like a good job to some extent, right? Because you've trained the model on the data that you're doing the comparison to. But if I took new data and I tried to estimate the result from new data, well, now I can say something about how well it does on how well the model performs on data that it wasn't trained on. And kind of, you know, in my opinion, this is a really sort of robust way of going about and getting like a good quality model. So there is a question. So when we think about this type of approach, though, there are kind of two questions that often come up, or issues. So it's always better to use available data and to testing data sets are not always available. So the only times where I've really seen in practice this thing where you have like a totally separate training set and a testing set is, or one of the few times that you see this happening is like in like data analysis competitions where you get handed a training set and then you have to compare against like a testing set. And fundamentally, the reason why that usually doesn't happen is because when you do have a good data set, you typically want to train your model on as much of the data as possible. And so this concept will look something like this. So I'm going to have training data. This will calibrate a model. And then here you will test the model against testing data. Okay. And now you can ask yourself, how well does the model do according to some of the metrics that we talked about, right? You could look at R-squared, standard errors, residuals, mean squared error. And what you're testing on, what you're really measuring in this case is, you know, how well the model is performing, and then you can maybe like recalibrate it. So that is kind of this principle of out of sample validation. So one example, one practical example that we're actually going to be sort of employing a lot in this class is k-fold cross-validation. And this is a particularly nice method that tries to work around some of those constraints that I was talking about kind of really leveraging your data. So the way that this kind of works is you have full data set, and what you end up doing is we're going to take our full data set and then we're going to chop out a piece of it. Okay, And so let's do this. So this is our training data. And then this little bit here is our testing data. So this gives rise to calibrated model. And then you can use this. What is the MSE of the testing data? And I'll kind of write it like this. And you can do this with different sort of randomly selected portions of the training data. So now I might, or sorry, of the full data set, not of the training data. So I might cut out a different portion here. And you can calibrate the model with a different data set, right? And then calculate the MSE here. And you can repeat this sort of many times, right? And cut out essentially different portions of the data. So let's do that. And then I can look at the average of my MSEs. And so this is one type of approach that can help you do some kind of model selection. And so I'm not going to talk about the procedure of the model selection, but let's suppose that the model that you're looking at is x1, x2, x3, something like this. You could do it also, you could do the same thing for like x1 plus x2 plus x4. And the question is, which of these two models is better? And then you can compare, so if this is model 1 and this is model 2, I can compare this metric for model 1 versus for model 2. Okay, and so conceptually, like, let's just think about what we're doing here. I am going to create a model of x1 plus x2 plus x4, and I'm going to do this k-fold validation. So you do this, k times. That's why it's called k-fold. So I'm going to take my full data set, take some amount of data out of it, run the model, and then look at the mean squared error against the training data set, right? And see how well it does. And then I might take a different model and do it against the testing set, see how well it does. And ultimately, what you are comparing is the ability of model 1 versus the ability of model 2 to do out of sample predictions. How close can I get to predicting the values in the non-trained data set out of sample in model 1 versus model 2, and then this is kind of like a standard way of doing the comparison. And so we will be talking about like approaches of how you could put in or select variables, because there's lots of different procedures of doing this. But fundamentally, the metric with which we decide to choose them are going to be either directly using k-fold cross-validation or some other form of cross-validation, essentially. The k-fold, formally what it does is you divide, you do this procedure k times, and you divide the data randomly k times. And so I am going to sort of write an algorithm sort of manually to do this, because it's actually such a well-known and sort of popular metric for doing predictions. A lot of functions will have this kind of built in, but I will, write out this function explicitly so that everyone can kind of see what's going on. And I think on the homework, you'll be asked to kind of replicate this as well. Okay, so let's hop on over back to RStudio, and I can show an example of this, unless anyone has any questions right now about k-fold cross-validation. All right. So I will kind of explain what's going on as I sort of type this out, but definitely this is going to be a slightly more complex equation, or sorry, not equation, more complex function. So, please also try to walk through these examples on your own to really make sure you kind of understand what's going on. Obviously, if you have any questions as we're going along, yeah, feel free to let me know. Okay. So what I'm going to do now in this first one, okay, this first line is sampling between 1 and the number of folds that I want randomly, and the number of draws it's going to do is equal to the number of rows in my input. Okay, so what does this mean? So let's just show a really quick example of what's going on here. So I'm actually going to be applying this to the wages model. So let's look at this. So we have wages here. And essentially what I'm going to do, let's say I want to do 5 folds. Okay, so note that we have 1379 rows in wages. So we're going to do 1, 2, 5, which is the number of folds. And again, this is just a demonstration of what this line of code is doing. So n row of wages, replace equals true. All this is doing is it's going to give me 1,379 values of numbers 1 through 5 randomly. And I'm actually going to go ahead and attach that as a new column to the input. So what that would be doing, so I'm just gonna do this really quick. I'm just gonna create a temporary data table to do this. So all it's doing is if I look at this table again, I've just added on an extra column of essentially randomly selected numbers 1 through 5. And because it's sampled, you should have roughly the same number of each of the individual 1 through 5s. And actually, as a handy tip for you guys, there's a function called table that will tell you this. So if I do temp index, this tells you the count of each of the unique values within a vector. So there's 257 ones, 252 twos, 304 threes, and so on and so forth. Okay, so that's the first 2 lines. I've just added on a column, and that column is going to act as my index. I'm going to create a blank vector, which will get filled in later. Okay, and now I have a for loop that's going to run the model for each fold. So if you think back to the drawing that I did before, like it's going to be 1 through 5, and each one is going to be essentially portioning out a piece of the data, running the model against what's remaining, and then testing it against the piece that I pulled out. And the for loop is just doing that, in this case, 5 times. So I'm going to create my training data, which is going to be this, which I'll tell you what this is in just a second. All right, so remember I had the big square and then I cut out a piece of the small square. So the training data is the big square and the testing data is the small square. And so if I look at this example, let's start with 1. So everything that has 1 in the index is going to get cut out. And so the way that you do that is training.data where index, okay, I'll write it out explicitly, where training data $index is not equal to 1. I need a comment at the end here. Okay, and so if I run this, remember in the full data set, we have 1379. And what I should be getting returned is 1379 minus 257. Okay, oh no. Should not be training data. Temp $index is not equal to 1. Okay, so that's 1379 minus 257, 1122. Great. So you'll see here that this is my full data set. I've carved out that square, the small square, so that there are no values equal to 1 here. And then conversely, I have testing data, which are all the ones that do equal 1. Okay, and there's 257 of them. Okay, perfect. So hopefully everyone's following along so far. And now I'm just gonna run my model, and I'm just gonna do one possible sort of combination of variables. Okay, so I am going to run my model of earnings regressed on height, sex, race, and education, and the data is going to be on the training. So it is only going to run on the big square, right, of the data minus that testing piece. I can then predict what the model would say are my earning values if I feed it the testing data. Okay, so this is going to tell me, so it's gonna run the model to figure out what the coefficients are for the variables in this model. And then it's going to, so I have height, sex, race, and education. So it's gonna take this value, this value, this value, and this value, and then it's gonna try and predict what the earnings are gonna be. And importantly, right, the model has not trained on any of this data. So it is an out of sample sort of validation. So then we can calculate the mean squared error of the predictions, which is going to be the mean of the testing.data $earnings minus my predictions. Right, so I have the real value, I have the predicted value from the model, and then I just subtract them, and then I square them, and then you do the mean of that, and that gives you the mean squared error. And then I will update the MSE.all. So what this does, so line 25 and line 32. Line 25 starts out with an empty vector, and then it's going to get filled in with the mean squared error of each of my folds. Okay. And then I'm going to return the MSE.all. So let's run this and see what happens. So if I do kfold.cv1, I will look at the input is going to be my wages data, and then the number of folds, let's just say 5. And this, oh, where do I have model.model? Oopsies, model.hold. Let's try that again. Okay, so you can see these sort of set of values here. Okay, so that's the average size of the error, of the squared error for this particular model. Now I can compare this against a different sort of model selection. I can, so I copied in a new function kfold cv2, and the only difference between this one and this one is that my model here is different. So here it's height, sex, race, and education. Here it's age, sex, race, and education. So I can attempt to answer this question about which of these two models, if I have height versus age and then the rest being the same, which of these two models does a better job at predicting values that it didn't train on? And so you can look at the average of the mean squared errors of all the folds. So let's do that. So kfold as a sort of most direct comparison. So it's just the same thing as I have above, but it's going to take the average of those. Oh, oops. Let me just do it like that. Oh, I didn't. Did I run this one yet? I did not. Okay. All right, let's do that again. So here's model 1, where you have height, sex, race, and education. And here's model 2, where you have age, sex, race, and education. And these are directly comparable. And so in this case, I might say that on average, K-fold CV1, in other words, the one with height, actually does a better job at predicting out of sample than with age. Okay. Any questions about this? Or confusion?
So after we select which model is better, how do we determine the coefficients? Do we calibrate the model again on all the data?
Yeah, generally that's how people do it. Is you basically say, okay, I'm confident that this model where I have these 4 variables is the best one based off of the ability to do out of sample prediction. And so now I'm just going to run it against the full data set, get the coefficients, and then, then you can kind of use that as the sort of final model.
Can I ask a question?
Yeah. Mm-hmm.
Do you usually compare model that only has one different variable like that, or
Yeah.
can we?
Yeah. So starting next class, we're actually going to talk about how you go about choosing the variables, because right now I've done this arbitrary thing where I just said, okay, compare this model to this model. But you could compare any sort of combination of variables. And so there are going to be a couple procedures that that help you systematically decide which variables to test, and it's not going to be this thing of like one at a time, or well, actually some of them will be, but generally it's a more sort of systematic way. And so this example is not to demonstrate how to pick the variables, which we're going to talk about next class. This example is to show how to compare the models using the K-fold. And so going back to this thought about how you pick the variables, it's actually goes back to the example that I was giving earlier, based on Sarah's question. It is actually a similar sort of difficulty, and why, actually once you start getting to sort of machine learning type things where you have many variables, they start to have more strict procedures about how to choose them, because if you are more versed in kind of the econometrics field, like we select variables kind of actually based on intuition. Like if you want to say, like, for example, okay, I mean, I do a lot of transportation work, and so the types of regressions that I might see are like, how are vehicle sales affected by like attributes of the car? And so the attributes might be something like, I would say, oh, okay, I think the price affects the sales, and like fuel efficiency affects sales and stuff like that. So choosing based off intuition. But in some like machine learning contexts, you may have hundreds, thousands, or even it's even possible to have like on the order of millions of variables. You can't sort of choose by that sort of method, and therefore you have to come up with a systematic way of being able to select variables. And those procedures are constrained in sort of the same way that we were talking about interaction variables. So actually, even if you don't have interactions, like x1, x2, x3, x4, right? The number of combinations of variables, like even without having this interaction issue, still kind of explodes very quickly. So all right, I'm going to double check this, but but I believe the growth rate is 2 to the n. So n is number of variables. I'll double check this, but this is kind of the number that I have in my head. Actually, let me see if it's in my notes really quick. Yeah, okay. Yeah, so okay. I mean, I'll make sure that I'll find the right sort of growth rate, but the concept that remains, which is that selection of the variable is in itself kind of an interesting problem, an interesting concept, because the combinations of what you would include in the model grow really quickly with the number of variables you have available in your data set. Yeah, and so, yeah, again, just to reemphasize, like, this is not the procedure with which you select the variables. This is just the procedure to demonstrate how you would compare the models.
One question here.
Mm-hmm.
In this k-fold cross-validation, can we use any other criteria than MSE? Maybe.
Yes. I personally prefer the MSE, and it's actually probably one of the most common ones. But we are going to talk about a whole bunch of different metrics next time that are also used. So the adjusted R squared, the AIC, BIC, and what's the other one? Mallow's CP. These are all other metrics that that are used as a criteria. Yeah.
Okay, thank you.
All right. Any other questions? Okay, well then we can end here for today. And then, yeah, so administrative stuff, as a reminder, homeworks are going to be due at midnight tonight. Yeah, so remember to submit, and then homework 2 will be posted on Monday, and then I will also introduce the course project on Monday, and let's start with that. And so if I forget to talk about it, you guys can just remind me to talk about the project. Otherwise, yeah, I will see you guys next week. And I'll stick around for just a couple minutes again if anyone has any lingering questions, either on here or if there are any last minute questions on the homework.